Okay, so I think we're live now. Mhm. And so today, on Wednesdays, I'm gonna make this like a regular thing. So my usual schedule is just like 4 p.m. So now it's like Tuesday, Wednesday, Friday. And Tuesday and Friday, I've been kind of like lecturing mostly and doing maybe like exercises just every once in a while. And Wednesday, I want to be like devoted basically the whole time to doing exercises, unless I need to like describe something important, like an important definition or something. Of course, if we have to go over a definition for a problem to make sense, then that's what we have to do. But so we got a couple questions in the Discord. Um, One was, or a couple from Offendum, which I really appreciate. These are some very good questions. So let me put those up on the board. Okay. So the first problem deals with still dealing with abstract vector spaces. So the first problem doesn't have anything to do with matrices yet, but let's still just tackle it anyways. So it says that we can see that the real numbers are a vector space over the rational numbers. So every real number, we can scale it by a rational number, right? But it turns out that this is infinite dimensional. So there is no finite linearly independent spanning set of the real numbers where we take coefficients in the rational numbers. And so yeah, that's the first problem. We basically want to show that that's the case. So show that R is infinite dimensional as a Q vector space. Okay. Um, Something that seems odd here is that it seems like R and Q are in some sense like taking up the same dimension, so it doesn't really seem to make much sense to say that R has like infinite dimension over Q. But I think that the important thing here to remember is that there's no inner product on these vector spaces, so there's no notion of like angles or orthogonality or anything. So when we say it's infinite dimensional, it's not really like infinite dimensional in like a spatial sense. It's just literally you know, the raw linear algebra definition. It just means there's no finite spanning set, right? Um, so yeah, why I can think of one reason this is true, but it's I guess I'm sort of assuming something that's not so obvious. I'm wondering what the viewers think of this question. How might we go about proving this or showing that this is true? So I can go through I can go through one argument. It's I would say quote unquote a little bit cheating, at least if I don't prove one of the statements. Um, but yeah, I'm curious if anybody in the audience has any ideas. So I'll write out my argument for this, but we'll discuss it a little bit. So so how I would argue here is I would say so assume for contradiction that it was finite dimensional, and then we'll write down some basis. Okay, so assume that it is finite dimensional. Write down a basis. Q1, Q2, Qm. right? And then this I would say is the step that's not so obvious. But if we take all linear combinations of some finite set of numbers, and we take all of those possibilities and we combine them all into a set, how big could that set be in cardinality? Well, since we're taking finite linear combinations of a finite number of numbers, this is the step that's not, I'm a little hand wavy about, but you can only get at most countably many numbers from this process of taking linear combinations, right? So if I look at all possible linear combinations of this, by assumption, if it's a basis, then R is all linear combinations of these numbers. But this is a countable set and R is uncountable. So that would be a contradiction. So if this is a basis, then that would mean that R is equal to all linear combinations. Of the QIs. And this is a contradiction. Right, because this is definitely, I'm not claiming that this is a full proof. So definitely, this step is not obvious how to prove that if I take all linear combinations of these finite set of numbers, that set can be at most countable. And then there's no way that it could be equal to R if it's at most countable. So this is sort of like a set theory argument in some sense, but I'm leaving out the set theory part of it. Can we think of a better proof? Maybe one that doesn't have like a gap in the argument? I'm wondering if anybody can think of one. We would have a bijection from Qn to R. Oh yeah, that's a good point. Yeah, that's essentially the same thing I was saying, but worded much better. Yeah, that's a good point. So Effendum says if every vector has unique coordinates with respect to a basis, we would have a bijection from the Cartesian product of the rational numbers to the nth power and the real numbers. But we know a finite Cartesian product, actually I believe even a countable Cartesian product of countable sets is still no, that's not true. Yeah, I think it's for finite you're good. Yeah. So q to the n, if you have a finite Cartesian product of countable sets, it's still countable, and therefore it can't be bijective to R. So that would be a contradiction. Yeah. Yeah, that's actually, it's essentially the same argument as this, right? Because here, yeah, that's actually kind of like the gap in the reasoning here. So really, you have to prove that a finite Cartesian product of countable sets is countable, and that's really a set theory proof. Once you have that, then you have this argument. Yeah, same thing as what Effendum said. So yeah, assuming we're not dealing with set theory here, I guess we can sort of hand wave that a little bit, but yeah, that would be I think that you have the main idea actually. Your understanding of it seems actually better than mine, because yeah, I think it's a lot easier to see that q to the n is countable rather than trying to argue that all of these linear combinations are countable. That might be slightly more tricky, but I think they're essentially equivalent to each other, so probably the argument is not much different anyways. Okay, so I think that deals with one. That was a good... That I think... Is there any other way to solve this without using some sort of set theory argument? Maybe we could try to argue that, using this basis, we could assume that this is every possible number, and then, maybe we can find a number that's in R that's not in this basis. Like, perhaps, like, pi is not... we can't actually, we can't write any irrational number. Right. Okay, yeah, that's probably a better way of saying this. So we have all rational numbers here, right? Every linear combination of these with rational coefficients is also a rational number, right? So there's no way that we could get pi or any irrational number, square root of 2. Existence of transcendental number. Well, not even just transcendental numbers, but any irrational number as well can't be in the span of these, because the span of these are Oh, sorry. These can be real numbers. Yeah, yeah, yeah. I'm confusing myself. Um, no. Transcendental numbers that doesn't do anything, right? Because yeah, but these numbers could be irrational. They could be transcendental themselves. So yeah, actually, I think you do need to argue the way we were just talking about because I'm sure there's probably another proof, but I think the set theory one's probably like the simplest to understand. Like you have a bijection of q to the n to r, and we know that q to the n is countable. So that's probably the simplest. What are you saying here? So every vector has unique coordinates. Yeah. Wait. We can we not show it with the existence of transcendental numbers? Pi is not the root of any finite polynomial with rational coefficients. Yeah, but pi is the root of like x minus pi, right? So we have to be a little careful. Because the coefficients could be like, yeah, these numbers don't have to be rational. I shouldn't have wrote q's here. Really, they should be r's. R1, R2, R3, R to the R sub m. Um, right. So, is there any argument that doesn't deal with the countability versus uncountability of the sets, or because really we're relying on some sort of set theory argument here? I'm wondering, is there any argument that avoids the set theory at all? Maybe there isn't. Maybe this is just the most straightforward way. Okay. Well, yeah. I mean, this was interesting to think about. So yeah, real numbers are a vector space over the rational numbers, but there's no finite basis. Because if there was a finite basis, all of these linear combinations would only get you to a countable number of terms, basically. And because the real numbers are uncountable, we know there has to be some sort of mismatch here. So there can't be a finite basis. Yeah. Okay, let's move to question 2, unless someone has anything to say about this one still. So this will be Offendum's second question. This one's a lot simpler. I think this first one was kind of a little bit speculative, but this second question's a lot more straightforward. Okay. Okay, so second problem, show that if we have a linear transformation from R to R is linear, then t of x is necessarily equal to c times x for some real number. Okay, so essentially what we want to show is that all we're assuming is we have some linear transformation between R and R, so these one-dimensional real vector spaces over themselves. Assuming this is linear, then we want to show that necessarily the function just multiplies every number by a constant. So every number x, we apply the transformation, we just get c times x for some number. That number could be 0, it could be non-zero. If it's 0, then obviously the function is not invertible. If it's non-zero, then it is. So this is kind of, in some sense, the simplest non-trivial linear transformations that are possible. The simplest one possible would just be you have the 0 vector space mapping to 0 in itself, but this would be like the first non-trivial thing that you could do with vector spaces. So why is this true? Well, we've been talking about the basis of a vector space, and the most important thing about a basis is that when you define a linear transformation, all you have to do is say where do the basis vectors end up. So for here, if we know that t is linear and we know that we have a basis for r, it's one dimensional, so the basis is just the number 1 or any non-zero number. And so to know what the transformation is, we just have to know where 1 gets mapped. So since t is linear and 1 is a basis, then t of x is equal to t of 1 times x. And then we're basically done because t of 1 is some number, and I'm using the linearity property to pull the x out, basically. So we have 1 times x here. And because x is a real number, and this is a linear transformation, I can pull the x out of the transformation. So t of 1 times x is equal to t of 1 times x. And since t of 1 is just some constant, then that's our c, and we're done. So we proved that t of x is equal to some constant times x. And that's it. That's all you have to do. So that's that. Any questions about this, Effendum? So basically, you just are assuming it's a linear transformation, and because of the linearity, you get a lot of rigidity in what kind of function it can be. Really, it's all just determined by where it sends the basis, and since there's only one basis vector, it's just determined by where you send that number 1. Okay. Squeaky board. Ah. Okay, and then we got a few problems in the Wednesday section on Discord from Dick Duke 613. And I chose the one that I thought was the most relevant because a couple of the other ones dealt with eigenvalues, which we haven't talked about yet. So I thought I would skip over those, but this problem seemed interesting and applicable because it deals with matrices. So this was number 3 in that homework little printable thing in the Wednesday, or actually it's in the Wednesday problem submission section, and this is number 3. It's the one he just submitted, I think, today. So this says let A be a diagonal matrix where all the diagonal entries are greater than or equal to 0. So they're non-negative. And then what we want to do is we want to show that if this is one of these types of matrices, then there exists another matrix B, which is in some sense the square root of A. And I'm saying this with a quotation because really there actually is a square root of A if it's a positive operator. And they're not really using this terminology, but if all of the eigenvalues are positive numbers and it's diagonalizable, then there exists this unique square root. But in this case, we're kind of avoiding all of this orthogonality talk and all of this more complicated math, which would come out up later in Axler, for example. And they just simply want you to find the matrix, which essentially is the square root. So we want to find a matrix B with the property that B squared is equal to A. Okay, and it's very important here to note that this isn't always possible. I believe there's matrices where there is no square root, and then there's other matrices I think where the square root is not unique. So there might be actually more than one matrix where the square is A. But if the matrix is representing a positive operator, which we're not really going to define here, but you could imagine it has something to do with this entries being positive here and it diagonalizable. In that special case, then there is a unique positive square root, and here, since this is the case, they want us to find that unique positive square root matrix B such that B squared is A. But I just wanted to point out that there's no reason that it has to be unique except for in this special case, and there's no reason that the square root even has to exist, I believe. It might not even exist. Maybe somebody could check me if somebody smarter than me is listening right now, but I don't think there always has to be a square root, and I don't think it has to be unique unless it's a positive operator, like in this case. But okay, so let's try to figure out what's going on. Right, so we have some matrix that looks like this: lambda 1, lambda 2, lambda n, and all the off-diagonal entries are 0, and we know that the lambda i's are all greater than or equal to 0. Okay, so I guess this is either obvious or not obvious depending on how comfortable you are with matrix multiplication. But for diagonal matrices, matrix multiplication is extremely easy. So for more complicated matrices, there's a little bit more computation involved usually. But all of these zeros on the off diagonal actually force some pretty simple math. So when you take any power of a diagonal matrix, all that happens is the diagonal entries just are raised to whatever power that is. So in this case, if we want a matrix whose square is A, all we have to do is take the square root of all these positive numbers, or non-negative numbers, and then when we square that matrix, then we'll get A. So really the solution is just take the square root of lambda 1, square root of lambda 2, and so a little bit of a boring answer maybe, or depending on your understanding here, but yeah, so all we do is take all the diagonal entries, we take the square root, then when we square this matrix, we just get the square of all the entries on the diagonal, so we get the original matrix A here. So if this is A, then this is B, and B is the positive square root of A. I guess technically there's also a negative square root, right? So you have to be a little bit careful about, yeah, actually there's a lot of square roots here, right? Because I can take any one of these entries and I can flip the sign on that one and its square is still A. So here there's one unique positive square root, but there's actually many non-positive square roots which have negative eigenvalues or negative values along the diagonal. Right, so you see here actually, so over the real or complex numbers, when you have a polynomial like this, or you have a relation where, the square of a number equals another number, there's at most 2 square roots of a number, right? But for operators, it's no longer the case here, because there's actually many different square roots, depending on which of these numbers we flip the negative sign on. Okay. Right, so let's get into the determinant of a matrix. Very, very, very important notion, which Axler pushes off to the end. Sometimes it makes sense to me, sometimes it doesn't. I want these videos and these streams to be accessible to a larger audience, so I definitely think determinant should be at least talked about. We should do a couple problems, a couple calculations here in the exercises, just to make sure that we're not completely lost. Or it also helps you in solving linear equations, because if you find out the determinant is 0, then you don't have to check if there's a unique solution or not. You automatically know that there's not a unique solution. So certain things like that, the computations of actually calculating the determinant, I think it's important to know how to do it, especially for newer students. So let's talk about the determinant a little bit. Okay, so this is going to be a definition. Determinant, hopefully I spelled that right. Determinant, right? Yeah. Determinant of a linear transformation well, really it should be of a linear operator. Meaning that the linear transformation is actually from a vector space to itself. Instead of from V to W, it's from V to V, right? So what is the determinant? So let T be a operator. So it's a linear transformation from V to itself. Be linear. And let's assume finite dimensional here. So V is finite dimensional. V is finite dimensional. So let T be a map from V to itself, finite dimensional vector space. Assume that it's linear. Then the determinant of T is equal to the determinant of any matrix of T with respect to any basis. So for any basis here. And let's say what the determinant of a matrix is. Okay, it's got this really annoying definition, which hopefully I'll try to justify in a little bit based on the properties that the definition has. So you're going to be looking at products of entries from the matrix. So you're looking at the index of the element, so it's I comma sigma I. So basically we're shuffling around the column that we're dealing with, and we're taking a product over one element from each column, one element from each row. I think you can actually define it either way. It's kind of got a symmetric definition in some sense. But yeah, you're iterating over the rows, and then you're shuffling the column entries, and you're taking one from each row basically. Here you have the sign of the permutation, so this is going to be 1 or -1 based on how many things we've transposed. So every permutation has a unique plus or minus sign based on the even or odd parity of the permutation, basically. Do I have this right? Yeah, and then, oops, sorry, we're going to be taking a product over all these. My bad. Hold on. This is not correct. It's going to be a sum over a product of the AI comma sigma I. Yeah. I had an index there that didn't make sense because the index wasn't associated with anything. But yeah, so determinant of matrix is a sum over all permutations in Sn. So all permutations of n things, there's n factorial of them. And then we take the sign of the permutation, and every entry of this sum is the product over all of these elements, where we're taking one element from each row and each column, but we're permuting which column it is by some whatever the permutation is at the beginning of the sum. All right, and so basically nobody ever uses this definition for anything. What you really want out of this definition is the fact that it's multilinear in the columns and the rows of the matrix. It's alternating in the sense that if you swap any of two rows or columns, you change this sign here. So that's the point of this sign term here, plus or minus. If this term wasn't here, then you wouldn't get this alternating effect when you swap the rows or columns. And some other important properties are when you multiply a row or column by a scalar in the field, then it multiplies the determinant of that matrix by that same constant. And so what we can actually do is that's probably the most important property of this definition here, is that it's multilinear and that it's alternating. So in other words, it scales. When you scale each row, you scale the determinant. And if you swap any two rows or columns, then you multiply the determinant by -1. Those are really the two most important properties, and from those two properties you can actually compute the determinant very easily without needing to refer to this bulky definition, because you really don't want to use this definition because you're doing a sum over permutations, and there's a lot of permutations. So if your matrix is 10 by 10, then you're summing over 10 factorial different permutations, right? So you definitely want to try to avoid this definition, and you can avoid a lot of these terms if any of these entries are 0, right? If any one of these entries are 0, then you can just ignore that permutation, and that makes your computation a lot easier in that case. Right, so the only thing about this definition, though, is it's not obvious that it's well defined, because I said here that I can pick any basis and calculate the determinant of the matrix, and I should get the same thing. But, I haven't made any sort of argument for why that should be the case. Maybe if I pick a different matrix, a different basis, and I write down the matrix for the transformation in different coordinates, it's possible that when I calculate this determinant using this definition, I would get a different number. But that's just simply not the case. But definitely not obvious. So, right. Is there any questions about this? This is just the raw definition. There's also a recursive definition using cofactor expansion, which I think is maybe sort of useful for 2x2, 3x3, and 4x4 matrices, but anything over that, I would just use the multilinearity property, your reduced row echelon form operations, and you can use those to recover the determinant, and you don't need to use this definition. But I think it is interesting to see the definition, and I don't know why Axler puts it at the very end. I think he could have put it at the beginning and then say, hey, we're going to justify this definition using the rest of the book, and then put it at the end also. But, oh well, he chose to do it the way he did. That's fine. Any questions about determinant? And then, so what are we determining here? What does the determinant determine? And that's the main idea here. So the determinant, if it's invertible in the field, or in other words, if it's non-zero, so if the determinant is not 0, then that means that your transformation is invertible. It positive. It is invertible. If the determinant is 0, then your transformation is not invertible. So it really is kind of like an on-off switch. You know, is it 0 or is it not 0? If it's 0, then no good. Your transformation is not invertible. If it's non-zero, then it is invertible. And you can actually figure out what the inverse of the matrix is using there's like this adjugate matrix. I think we were talking about it with Slim earlier. You can write down the adjugate matrix, and then it's like 1 over the determinant times the adjugate matrix is the inverse of the matrix. So there's this whole story where you can actually explicitly write down that in that case. But for that formula, you have to divide by the determinant, so the determinant has to be non-zero, is the moral of that story. Okay. Okay, yeah, so let's just compute. So this is in Anton. So shouts out to Penn Center. He suggested this source. So this is Elementary Linear Algebra 12th edition. And this is section 2.2, exercise 23. And it says use row reduction to show that, and then, so you should get comfortable with this notation. If you put straight bars instead of the brackets, like a normal matrix, then that just means the determinant of the matrix. So it's going to be flat bar 1, 1, 1, A, B, C, A squared, B squared, C squared, and that this determinant, or maybe I'll just write determinant here. So the determinant of this matrix is B minus A times C minus A times C minus B. Any questions about determinant or what this question is asking for? So A, B, and C are just some elements of the field. I guess they could be any elements. Here, since we're dealing with Anton, they're probably just real numbers. This is like an introduction book. Right. So the point here is that we can apply these, they're called elementary row operations, so we can either multiply a row or column by a constant. I can add a row or column, or any multiple of a row or column to another row or column. And I can also, now I'm blanking out, what's the last? So you can scale a row or column by a constant. You can add a multiple of one row to another row or column. And there's one other thing we can do. So what else can we do? Subtract, multiply. Or we can swap two rows or columns. Right. So each one of these elementary row operations, it does something to the determinant. Well, actually, one of them doesn't do anything. But I was saying before, if you swap two rows or columns, you get this sign change. So If you swap two rows or columns, you change the determinant by multiplying by -1. And the other way to change the determinant is to multiply a row or column by a constant. In that case, the determinant also gets multiplied by that constant. So essentially what we have to do is we're going to try to reduce this matrix into reduced row echelon form. Essentially, we're going to try to create many more zeros. I don't want to go into like writing down the full algorithm because it's actually sort of complicated to precisely formally write it down, and I don't want to waste the board space or the time doing that. So I would say if you are confused, if you've never heard of reduced row echelon form of a matrix, I would just pause this and maybe look it up, in Google, or look up another YouTube video about it real quick. But essentially that's what we're going to do here. We're going to eliminate this a and this a squared here. Then we're going to normalize whatever factor we have here, and all along the time we're going to be keeping track of every time we multiply a row or column by a constant, and we're going to remember that the determinant is going to be affected by that change, or that by that scaling factor. Okay, so that's essentially what we do. So we want to eliminate this a and this a squared. So one way to do that is I can subtract a times the first row from the second row, and I can subtract a squared times the first row from the third row, and that will, once I do that, that'll be a minus a, this will be 0. A squared minus a squared, this will be 0. So yeah, let's do that. So it'll be 1, 0, 0. Then we have b minus 1 times a. So this is b minus a. And then we have b squared minus a squared. And then we have c minus a and c squared minus a. Okay. So because I went from this matrix to this matrix only by performing row operations which are adding or subtracting some multiple of another row to a different row, and I said before that these operations don't change the determinant. So the determinant of this matrix should be the same as the determinant of this matrix. And because we've introduced these extra zeros, it actually becomes easier to calculate the determinant of this smaller matrix. And it becomes very easy if the whole matrix is upper triangular or lower triangular. So in this case, we're going to keep doing these row operations until the matrix is completely upper triangular, and then the determinant is just the product of the diagonal entries in that case. So that's what the process is. So here, now we're going to continue. I'm going to take the second row and multiply it. So I want to get a difference of squares, so I have to multiply the second row by b plus a. Or, oops, wait, wrong part. So I want to subtract b plus a times the second row, because that'll make, so then we'll have b minus a times b plus a. That'll give us a difference of squares here. And then when we subtract it, I'll end up with a 0 here. And then our matrix will be upper triangular. So that's the goal here. So this is 1, 0, 0, 1, b minus a, 0, because that was the point. And now finally we have 1, c minus a, and the last entry is c squared minus a minus the quantity b plus a times the quantity c minus a. So it's going to be a foiling. You're going to have to like foil it out. It's going to be c squared minus a. Right. I did all the math out here though for you. Right. Just have to simplify it a little bit. What is it? So it's c squared. Oh, I forgot it. There's the a squared here. Oh, E times A. Oh, no, I did that. Wait. Gotta check my work for a second. Hold on. So we subtracted A times the first row to get these two zeros. Then we subtracted A squared times the first row to get this 0. So we got A squared. Yeah. Subtract A squared. Okay. I'm good. Right. So here's the part where we need to, yeah. So it's C squared minus A squared minus the quantity C minus A times B plus A. And if you do that out, you can see that there's actually a minus a negative A squared here, so a plus A squared. So the A squareds cancel. You have a C squared, and then there's like a couple other cross terms. So you can check my work here, but I believe in the end you just get C squared minus B times C plus A times B. So it's C squared minus BC plus AB. So just to read the entries here, if you can't read it, I'll read the columns down. So it's 1, 0, 0 is the first column, 1 B minus A 0, and then 1 C minus A, C squared minus B times C plus A times B. And now we're almost done because, well, now it's upper triangular. So I said that the determinant was easy to calculate in that case because of all these zeros, and it was just the product of the diagonal entries. And so now we know that the determinant of this, which is equal to this, which is equal to the original thing, is just the product of the diagonal entries. So it's 1 times B minus A times C squared minus BC plus AB. So B minus A. And then if we factor what this is at the end, it's really just C minus, what is it? C minus, yeah, C minus A times C minus B. Right, because you have the C times C gives you the C squared, negative A times C gives you the, oh, do I have it backwards? I might have it backwards. C, do I have the signs messed up? Maybe it's C squared plus BC? Or no, plus, oh no, this is right, yeah. Minus A times minus B is positive AB, minus A times C, oh, I guess I wrote it, did I have it wrong? C minus A, yeah, I probably just messed up this part right here, so this should probably be, here, let's just check again. So C squared minus A squared minus, so the A squareds cancel, we don't need to worry about those, and we just get minus, so it's C times B, so minus C times B term, yeah, so C squared minus B times C, and then we have a minus A times minus A, or sorry, that one already canceled, and then minus B times, yeah, so plus AB. And then that factors as C minus A, C minus B. Wait, why is there an AC term? Something looks wrong here. Oh, I'm multiplying by B plus A. It should be C plus A. Oops. Oh, no, that's correct. Okay, yeah, I'm just trying to figure out why this term is correct. Or not correct. Let me just fix this. Okay, so C squared minus BC. I think I just wrote this. This is just a typo at the end, right? C minus A. C minus B. Oh, no, that is what we want to show. B plus A. C squared minus A squared plus A squared. C squared minus BC plus AB. That seems right. But then, so B minus A times C squared minus BC plus AB, that factors as C minus A, C minus B. C times C is C squared. C times negative B is minus BC. Negative AC. Yeah, where does the negative AC term go? That's the thing. Negative AC. Huh. So how does this factor? So C, I'm sure that's right. There should be 3 terms here, right? I'm missing a term. Okay. Yeah, because the A squared terms cancel, but then I'm still missing. So it's minus BC plus AB and then plus A squared, but also right. Plus AC. Right. That's the term I'm missing. Okay. Sorry. Right, and then if you have the plus AC, then yeah, okay, now we're good. So, yeah. I think the sign is wrong. So minus AC? Yeah, minus AC. Okay. All right, sorry about that. Right. So we're doing row operations. We subtract multiples here to get these 2 zeros. Then we subtract B plus A times the second row to get this 0 here. And then we have to keep track of all the algebra here to figure out what this last term is here, but it should be C squared minus BC plus AB minus AC, and that factors as C minus A times C minus B, and that means that the determinant is the product of the diagonal entries, which is this factorization, this product. Okay, sorry about that. That is good there. So we showed that the determinant of this matrix is this product by performing row operations, getting it into upper triangular form. Once it was in upper triangular form, then we just took the product of the diagonal entries, and that was the determinant, and we factored it, and we got this. Anybody in the audience questioning this? Okay, and then I'll skip over this next part, but I just want to mention again that this determinant, if it's not equal to 0, then the matrix is actually invertible, or in other words, the linear transformation is also invertible, meaning it's 1-to-1 and onto, so you can do the transformation, and then you can go backwards, and there's invertibility there, so you can keep going. It's like a group in the sense that the operation, you can undo it. Right, so this is all determined by the determinant of the matrix, or the determinant of the linear transformation, if you want to think of it abstractly. And okay, so just for the last few minutes, let me go through an example of an algorithm. How do we compute the inverse of a matrix? So if we have a linear transformation, we fix a basis, we get some matrix for that operation, or for that operator, or that linear transformation. And how do we figure out the matrix of the inverse in that same coordinate basis? So this is one way, by sort of like a method by hand, where you can actually compute things and do everything on the board or on paper or whatever. Right, so let's find the inverse of this matrix. This is also an Anton, so same book, Elementary Linear Algebra. Anton. And this is page 58. This is one of the examples. So this is example 4. And we're given a matrix A, which is 3 by 3. Oh, also, by the way, because invertibility requires the domain and the codomain to be the same dimension, when you write down the matrix for an invertible linear transformation, it's always going to be square. So it'll always have the same number of rows as the number of columns, and this is necessary. If it's not square, then the matrix won't be invertible. So in this case, we have a 3 by 3. And we want to find some other matrix A inverse, such that A inverse times A is the identity matrix. And also in that case, it'll also be the other-sided inverse, so this will also be the identity. And so there's a method. I'll probably not have enough room here, so I'll probably have to erase at some point, just because there's so many numbers to write down, but there's a method where basically we take this matrix and we stick it next to the identity matrix, and then we perform the same operations on the left side as the right side. So everything we're doing to undo this matrix and convert it back into the identity matrix, we're going to have an identity matrix on the other side, and we're going to perform all the same operations on the other matrix. So we're going to basically keep track of everything that undoes the first matrix, and everything that undoes the first matrix is going to be on the other side in the keeping track of what A inverse is. So essentially what we're going to do is we're going to augment the matrix. We're going to have A on one side, and then I'm going to put the identity matrix on the other side, and then we're just going to keep performing row operations until at the end we're going to have in the end, we're going to have an augmented matrix, which is the identity on the left, and then A inverse on the right. And that's going to be so everything in the middle here is going to be this reduced row echelon form algorithm. But that's just a fancy language for saying we're going to perform row operations. So basically the same process we just used for the determinant in the last problem, where we're creating zeros by adding or subtracting some multiple of a row to another row. We're going to do the same thing here, but we're going to have this augmented setup where we have A on the left, identity on the right, and then we're going to perform operations till the left side becomes the identity and the right side you can prove is the inverse. Okay, so that's essentially the setup. Let's switch maybe markers. Maybe black works here. So yeah, let's set this up. I'm gonna try to write it a little bit smaller, just so it can fit as much as possible. Okay. So here is our augmentation. A on the left, A inverse on the right. And now we're just going to perform these row operations. So I have 1, 2, 1 here in the first column. My goal is to get 0 and 0 here. So I'm going to subtract 2 times the first row from the second row. And I'm going to subtract 1 times the first row from the third row, so that this becomes 2 minus 2, and this becomes 1 minus 0. And all the other coefficients become affected as well, but I have no control over those. All I'm trying to do is create a 0 here and a 0 here in the first row. So I'll subtract, my notation for subtracting a multiple of a row is, I'll write next to the row, I'll write like minus 2 times, and then in Roman numerals, I'll write the number of the row. So it'll be like minus 2 times the first row, minus 1 times the first row. And now once I perform these two row operations, I'll get a new augmented matrix where, yeah, I just do everything according to the operation. So when I subtract 2 and subtract 1 here, I get 1, 0, 0. I get 5 minus 2 times 2, which is 5 minus 4 is 1. And then notice the first row is not affected, so this is still 1, 0, 0. Now I have to do a lot of mental math in my head. So 5 minus 4 is 1. 0 minus 2 is negative 2. 3 minus 6 is negative 3. 8 minus 3 is 5. Minus 2. 0. Oops. Minus 2, 1, 0, minus 1, 0, 1. Okay. So now that I've eliminated the zeros in the column with this leading one, now I go to the next column. So I want this 1 to be a leading one, so I'm going to eliminate this 2 and this negative 2. So I'm going to make those 0 by subtracting 2 times the second row and adding 2 times the second row to the third row. So I'm going to subtract 2 from the first row and add 2 to the third row. So 1, 0, 0, 0, 1, 0. And you can see if the matrix is invertible, the left-hand side should be sort of like slowly changing into the identity matrix. So the first two columns now are the columns of the identity matrix. The only column that's not is the last one, so we still have a little bit more to do, but yeah, so that'll be that. So negative, what am I doing? Yeah, so second one doesn't change. And now the first row is going to be 3 plus 6 is 9. 1 plus 4 is 5. 0 minus 2, negative 2. And 0 minus 0 is 0. Negative 1 plus negative 4 is negative 5. 0 plus 2 is 2. And 1 plus 0 is 1. Oops, I forgot this one. So 5 plus negative 6 is negative 1. All right, so we're almost done, right? This is just basically one more step. We just want to get zeros here and here, and then this will be 1, 1, 1 down the diagonal. All else are 0, so this will be the identity matrix. Let's make sure this matches with my notes. Make sure I didn't make any mistakes so far. So top is 1, 2, 3, 1, negative 3. Right. Oh, I did it in a different order. Okay. All right, well, we'll see if I get the same order, or we'll see if I get the same answer as the book, because I think I did it in a different order. But that's fine. So now I'm going to divide the last one by negative 1. So let me just flip all the signs here. So we divided by negative 1 here. I'll just write that in so we don't forget. So we divided the third row by negative 1. So we flip all the signs. This becomes positive 5. This becomes negative 2. This becomes negative 1. And now we're going to add 3 times the third to the second one to eliminate this negative 3. And we're going to subtract 9 times the third to eliminate this positive 9. And in the end, this left-hand side will be the identity, right? So we're going to get identity here. And so I'm not gonna write the identity matrix here. Let's just concentrate on A inverse. But for A inverse, we're gonna take 5 and we're gonna subtract 9 times 5 here. So 45 negative 45 plus 5 is negative 40. Negative 2 minus 9 times 1 is negative 11. Or sorry. Wait, negative 2. Oh, I'm doing the wrong one. Okay, so negative 2 minus 9 times negative 2. So positive 18 minus 2, which is 16. That's right. Oh, yeah, okay. Let me rewrite this. This is too messy. Let me just do it over here. This is probably better. Now that we have more board space, right, Rex? I've been rated, thank you. Yeah, just not going for too long today. We're just doing exercises, but I appreciate the raid anyways. Probably be over in a couple minutes, but we're just doing some matrix calculations here. So we've gone through like the theoretical part of Axler, and now we're dealing with the computational part, which is given a linear transformation, we can write down a matrix, we can calculate a determinant, and the determinant tells us whether or not the matrix is invertible. Now we've been going through a process of computing the inverse of a matrix by augmenting it with the identity matrix and performing a bunch of row operations. So we're at the last step. We're trying to get this left-hand side to be the identity matrix, and it almost is. We just have to perform these two more row operations, and then, yeah. So basically on the last step, we're trying to compute the inverse of the matrix. So now we basically have the identity matrix on the left, and on the right, it's augmented by negative 40 we just computed, then it was 16, and then we get 9, so that's 0 minus 9 times negative 1 is positive 9. 13 here, this is, yeah, negative 2 plus 15. Yeah, 13. Then we get 1 plus 3 times negative 2, so 1 minus 6 is negative 5. And 0 plus 3 times negative 1 is negative 3. And you can see why these problems are a little annoying. It's just a lot of arithmetic, right? So now the last row doesn't change, actually, so we're pretty lucky here. Right. And I did, in fact, get the same answer as the example in Anton by checking it. Even though we did the row operations in a different order, the inverse is actually unique for a matrix, so there's only one answer that I could possibly get, even if we go about it a different way. But yeah, so now this is the algorithm. So the algorithm says we stop here. This is the identity on the left, and whatever we have on the right augmented, that's the inverse. So this is the inverse matrix. So here's our A in blue. Here's our inverse matrix, and we can kind of ignore the identity. That was just useful for computational purposes. Thank you, Zach, for the raid again. Kyler. One message was deleted by moderator. What was that, a spam message? Oh, viral. Yeah, viral braggart. Okay. All right. Yeah, so I think I actually have to go soon because it's getting cold. It's really cold out here, by the way, and the chickens and the ducks are very affected by it. So they need some food and they got to go to sleep. So I think I have to go soon, but who should we raid? Is there anybody? Well, I'll take the raiders from here and I'll re-raid them to someone else. Who Who should we raid, guys? Also, if there's any other questions about matrices, let's raid n simplex again. Yeah, we got OB. Okay. Raid n simplex, and I love his name too, n simplex, right? So we got algebraic topology here. Pachinko. Da, da, da.